Welcome back. In the sixth video, we're going to bring back our op amps, but we're going to look at it through a different lens. Now recall that an op amp is this 5-terminal device here, where we've seen that VI1 is the non-inverting input, also commonly called V+, and then we have VI2 being the inverting input, given by V-. We have VS plus and minus, which are the supply or saturation voltages, and then our output voltage is Vout or V0. Now, we had some basic rules, but realistically, op amps follow a more generalized rule, where we have the output voltage equal to the differential gain times the differential voltage plus the common mode gain multiplied by the common mode voltage. And again, we defined our differential and common mode voltages in the previous videos. And if we really get into it, op amps are differential amplifiers. Now, in the extreme cases, we may say that the input impedance is equal to infinity. Our differential gain, which now we're going to call our open loop gain, that's going to tend towards infinity. Our output impedance tends towards 0, and our common mode gain is 0. We're also going to assume that we have infinite bandwidth, so we have the same operation across all frequencies. And this allows us to say that our output voltage is simply our open loop voltage gain times the differential voltage. Now, this video may get a little bit controversial, but we'll get to why that is in a little bit. Now, if we take our open loop gain to infinity, well, then our output voltage becomes pretty straightforward. If the differential input voltage is greater than 0, that output voltage is going to try to push towards infinity, and if it's less than 0, it's going to push towards negative infinity. But we know that we are capped by our saturation or supply voltages, so what we end up getting is the following graph here, where horizontally we're looking at the differential input voltage, and vertically we're looking at our output voltage. Now, it's not really the case that our open loop voltage gain can be infinite. So let's consider the case where the open loop gain is approximately 10,000. We can say that the output voltage is then going to be equal to 10,000 times that differential input voltage, Vi1 minus Vi2. And if our supply or saturation voltages will be plus or minus 12 volts, and our input differential voltage is, let's say, 1 millivolt, well, by our equations, our output voltage is equal to 10 volts. Now, 10 volts is not equal to the positive saturation or supply voltage, so we didn't really follow this up here. And if we look into it, we can say that the differential input voltage is equal to the output voltage divided by that open loop voltage gain. And if we want to see where we start to get that saturation, well, we just set that output voltage to Vs plus or Vs minus. So now if we plot this at a zoomed in scale, we can see that we have this small linear region, which is 2.4 millivolts of range. Now, a 2.4 millivolt range is pretty small. It's going to be hard to really not pick up noise and have it interfere. So what we really want to do is see if we can increase that linear region, and this kind of branches you into something called the summing point constraint. And I don't like how this is portrayed in textbooks or Google or even ChatGPT. You get a few bland sentences, which I've never even found to be helpful. But often the case, to extend this linear region, you often hear that you need negative feedback. And if we need negative feedback, the first question that could pop into your mind might be why. Why is positive feedback not good enough? And this is where we're going to get a little bit controversial in the discussion of this, because I kind of came up with a way that helped me in school. Perhaps someone in the comments and, the distant future may say that this is completely nonsense, but the point is to start the conversation to get to some point that's a lot better than these few sentences you find in a textbook that don't really explain anything. So what we're going to do is consider a positive feedback op amp. Now, the internals of the op amp are generally given like this, where it looks a little bit like our differential amplifier. This is not what's in the op amp. I want to make that very clear. This is just a representation. So we have some input impedance, some output impedance. We have a dependent voltage source, which is going to be equal to that open loop gain times the differential input voltage. We have our V plus and V minus. At the input, we have some feedback resistor, RF, some output voltage, and then we label our currents as we did here. So what we're going to do is consider this node right here by Vi1, and we are going to set up a KCL. Now the KCL is going to say that the current going in, so I1 plus IRF, that's going to be equal to the current going out of this node, which is I plus. Now for this example, we're going to say that VI1 is greater than VI2, or that the differential input voltage is greater than 0. Now we can expand IRF simply as the output voltage minus the input voltage right here, divided by our feedback resistor. So we get this term here. And we can express I plus simply as VI1 minus VI2 divided by this input impedance right here. Now, what we can also say is that IRF, which is this current, is equal to the current coming out of the amplifier per se. And that's going to be equal to the open loop gain times that differential voltage minus this output voltage right here, divided by our output impedance. So that's this equation right here. So we're going to substitute what we found in this equation for the current for the feedback resistor, set that equal to this current value that we found for the feedback resistor, and we're left at this term here. Now we can rearrange that term to look something like this, and we can take that even further to get what our output voltage is equal to. Now, we know that this term here is equal to VID, or our differential input voltage, and what we can really say is that for any increase in that differential voltage, well, we know that this term's not going to be negative, so for any increase here, the output voltage is also going to increase. Now we're going to jump ship and go to the negative feedback network, so it looks a little bit similar. We set up the same KCL around the node here. Now if we carry through as we did before, we end up at this equation here. And again, what we see is that if the differential input voltage increases, then our output voltage will increase. And now we can compare the positive and negative feedback networks. Now they look fairly similar here. Either way, if the differential input voltage increases, the output voltage will also increase. Now if the differential input voltage tends towards 0 or pretty close to each other, well, what do we get? We get that the output voltage is equal to either VI1 or VI2, and then we get this resistor combination here. Now this looks a little bit familiar to what we've seen in circuit analysis, but it kind of appears that no matter the feedback network you use, you get this same result. And this is the thing that kind of bothers me. There's not many answers for it. So maybe we're overlooking something. So we're going to keep the case that the input impedance is quite large, say it goes towards infinity, and the output impedance is equal to 0. And we're just going to set up a circuit like this, where we're going to plug in some sources, V2 and V1. We're going to have some source impedances, in this case they're just resistors. We still have our input voltages to the op amp, and we have our feedback resistor. Now we're going to say that the output voltage is equal to the open loop voltage gain multiplied by that differential input voltage. And if we look at what's in the internals for an op amp, this is what you might actually expect. Now, it's not the same for every op amp, but it's a lot better representation than what we had up here. Nevertheless, we're going to consider this kind of in a timing diagram. So let's say at t equals 0, we're going to call that differential voltage, that's going to be equal to plus epsilon, which is, let's call it some positive value. Now, because we have a bunch of stuff in this circuit, which is in the op amp, we're going to say that there's some delay between the output to input, such that if we have the differential input voltage as plus epsilon, where here it's the differential at the input, well, we're going to say that the output comes after the differential input voltage is quote unquote red. Now, if the input impedance tends towards infinity, well, we're going to say that the current going into this positive node here is going to be equal to 0. So then we're going to say that the system evolves like this, where we have our output minus VI1 divided by that feedback resistor. So that's this current right here. That's going to be equal to VI1. So again, that input voltage minus the source voltage V1 divided by RS1. It's going to be that current there. So we can rearrange that to look something like this. Or we can isolate the input voltage at the terminal for the op amp. And because we're looking at kind of a timing diagram, we're going to say that that is some function of t. That's going to be equal to this term here. Now, if the differential input voltage at t equals 0 is plus epsilon, or we can just call it epsilon and assume it's positive, we can see that the input voltage is equal to this open loop voltage gain times epsilon, that resistor combination, and that extra term. We can say that Vi1, or that input terminal, is approximately equal to the open loop voltage gain times epsilon times delta. So both of these are quite small, plus V1. Or we can express that as that first term plus Vi1 at time equals 0. And what do we pull from this? Well, as a function of time, that input voltage at the terminal of the op amp is increasing. So it's always going to be greater than the previous time. So you're going to have this ramping up that occurs. So if we have positive feedback, we get this runaway effect per se. Now, if we pull open a circuit, so what I have here on the left is a standard op amp with positive feedback, just some typical values, nothing crazy. And in the red line here, we are looking at the difference of the input terminals of the op amp. In the box here, you can see what the value is. And in the green here, we have the output voltage. So if we scroll all the way to the left, you can see that initially we start with the differential input voltage being extremely tiny. And as we start to ramp that up, you can see that the output voltage starts to run away, as we kind of predicted. Now, if we consider the case where we have negative feedback, and we're going to set up the exact same thing, what we get is that Vi2, again, that's approximately equal to the open loop voltage gain times epsilon times delta plus Vi2 at time equals 0. So what we can see is that as time evolves, Vi2 increases just slightly. But the important thing is that the differential input voltage is equal to Vi1 minus Vi2. So if Vi2 is increasing, it means Vid, or the differential input voltage, is going down. And we know that if this value right here, which is equal to the differential input voltage, if that's going down, well then the output voltage is also going down. And what we really end up with is that this feedback resistor, when we use negative feedback, it tries to close the gap per se. And that allows us to control the linear region a lot better. That's when we end up with our rules, where we can make the approximation that the input terminals to the op amp are about the same voltage and that no current goes in or out of the input terminals. And if you found this video useful, please like, comment, subscribe. Helps the YouTube algorithm. Thank you. We'll see you in the next video.